Welcome back to Math 160. I am going to finish our Unit 9 notes. That way we have all of our guided notes completed for the course. Very exciting. We left off on page 13 of our Unit 9 notes, practice number 6. Let's continue this and hopefully everything makes sense. Again, as always, if it doesn't, please reach out to me. I'd be happy to break it down further. Let's check it out. A survey of 61,649 randomly, I'm going to underline this, chosen people were asked several questions about office relationships. Whoa. Of the respondents, 25.5% reported that bosses scream at employees. How insane, right? Use a 0.05 significance level. Right there, we see that our alpha is 0.05 to test the claim that more than 20% of all people say that bosses scream at their employees. Totally unacceptable, but it's crazy that this happens. So we see that 61,649, that represents our N. We're going to go ahead and write that down. We are also, we noticed that of the respondents of that survey, the proportion that reported their bosses screaming at employees is 25.5%. So that represents our p hat, right? It's the sample proportion. So we're going to write that as a decimal as always, so 0.255. We see that we want to test the claim that more than 20% of all people say bosses scream at their employees, which means that the population proportion is going to be 0.20 or simply 0.20. It's up to you how you want to write that. If P is 0.20, we see that Q must be 0.80, something to keep in mind. We want to do a requirement check. Notice first that we have a simple random sample. We also want to check that N, the number of survey respondents, multiplied by the population proportion, so the P value, our success value. We want to check that that is greater than or equal to 5. Yes, that is satisfied for sure. Same thing, we want to check that N times Q is also greater than or equal to 5. And yes, in fact, it is. We know this is a binomial. We're essentially looking at a binomial distribution, but using the normal distribution to approximate, because we have two outcomes. Either they scream at them or they don't, right? Perfect. We want to determine the null and alternative hypothesis. So the null hypothesis is business as usual, that the proportion of people saying that bosses scream at their employees is 0.20, so 0.20 or 0.20. And then we want to test the claim that it's actually more than that. It's more than 20%. So we want to write that P is greater than 0.20. Noticing the P is greater than 0.20 tells us this is definitely going to be a one-tailed test, specifically a right-tailed test. So we want to calculate the test statistic. We use our previous formula, and I'll write it here again just so that we have it. Z is equal to P hat minus P divided by the square root of P times Q all over N. So we're just going to plug in our values. P hat is 0.255. Our P value is 0.20 divided by the square root of P times Q, so 0.20 times 0.80 divided by N, and N in this case is 61,649. When all is said and done, the math that you actually get, as crazy as this is you find that your Z-score is 34.14, which is way over here. Right? It's like boop, all the way over here. I mean, I know it's way longer, but we're just going to say that. So essentially, we want to know the probability that wow, I can't even talk today. I'm struggling. We want to know the area under the curve that's greater than or it surpasses a Z-score of 34.14. So we want to know this area here. Recall that when we looked at our Z-score table, if we ever had a z-score value greater than 3.9, we would actually say that the area to the left is 0.9 repeating. So the area to the left, which would essentially be the entire curve practically, is going to be 0.999. We're going to round to the nearest 10,000th place, right? So essentially 4 places after the decimal. What we want to consider, thousandths place. What we want to consider is the area to the right, above. So we're going to do 1 minus 0.9999, which implies that the probability here, that p-value, that probability, so I'll write that the p-value is going to be equal to 0.0001. We're always going to use 0.999 for values greater than a z-score of 3.99. Anytime it's greater than that, you're going to use 0.999 4 places, and then you just subtract from 1 to find the area to the right. So we see that our p-value is 0.0001. We're going to write that here for part D, determine the p-value. So the p-value is equal to 0.0001. Next, we want to write our decision about the null hypothesis and explain how we arrived at it. So we are going to compare the p-value with our alpha. Our p-value is 0.0001. Our alpha in this case is 0.05. We see that our p-value is definitely less than our alpha. So our decision is to reject the null hypothesis. Remember, if the p is low, the null must go. So we reject the null. So we're going to write our conclusion. There is sufficient evidence at the 0.05 level of significance to show that p is greater than 0.20. And then we can say the proportion of people who report their bosses screaming at their employees is more than, and we could say 20%, we could say 0.20, whatever you would like. Either will totally work. So it's more than 20%. Discuss the type of error you could have made. Remember that that means we're going to go back to page 4 of our notes. Recall that our decision was to reject the null. So if we go back to our table on page 4, we're going to start here. If you notice, we rejected the null. According to our work, we rejected it. So if we reject the null, we could have made a type 1 error. All right, which is alpha in this case. If we fail to reject, then we could have made a type 2 error, but that's not the case. So if you've rejected the null, we could have made a type 1 error, which means the null hypothesis was actually true, even though we rejected it, right? So that could have happened. So we are going to write, we could have made a type 1 error by rejecting the null hypothesis when it was actually true. That could have happened. Perfect. Using that table on page 4 is going to be super helpful. Remember to go back to that anytime you need, if you just want to make sure you're identifying the correct error. Okay, use that table on page 4. Practice number 7. Use the following Minitab printouts, answer the questions that follow. The claim is that less than 65% of all people feel they have saved enough for their retirement. Notice, here's your test and your confidence interval for one proportion. So your p-value is equal to 0.65 versus your p is less than 0.65. So right away, I want you to notice that here's your null and here's your alternative hypothesis. Okay. Notice here we have our p-value. That's going to be really, really helpful. And then notice we're looking at the 98% confidence interval, which implies that what's left over is 2%. So my alpha is 0.02. That's based on the 98% confidence interval. So we are going to state your decision and conclusion and explain how you reached it. As always, you want to compare your p-value with your alpha. Our p-value in this case is 0.193. Our alpha is 0.02. We see here that our p-value is greater than 0.02. So our decision is to fail to reject the null. I don't want it to be that close. So fail to reject the null hypothesis. And then we're going to write the conclusion. There is not sufficient evidence at the 0.02 level of significance to show that p is less than 0.65 or that less than 65% of all people feel they have saved enough for retirement. Or their retirement. And we're done. That's all we essentially had to say. We wanted to look at the printout. So given the information, we can assess the alpha, the level of significance, and then we look at the p-value. We can also see information about the null hypothesis and the alternative hypothesis. We see here that this is a left-tailed test, which is awesome, but really not anything that we have to worry about because we were given all the information here. When we take a look at part B, the claim is 52% of all library books are returned on time. So we see that our null hypothesis is that p is equal to 0.52 versus p is not equal to 0.52. So here's our alternative hypothesis. Notice it's a two-tailed test. We're just trying to see if it's different than 52%. So it's not equal to, right? We want to see if there's a difference here. Is there a significant difference? Notice our confidence interval is 95%. Because our confidence interval is 95%, we see that our alpha is 5%, so 0.05. We also notice that we are given a p-value, 0.000. So same thing as before, you are going to compare the p-value with your alpha. Your p-value is 0.000. Your alpha is 0.05. And we see that definitely the p-value is less than the alpha. So we're going to reject the null hypothesis. Having said that, we can now write our conclusion. I'm going to pause the video, write it out, and then resume. And we can say there is sufficient evidence at the 0.05 level of significance to show that p does not equal to 0.52, or that the proportion of all library books returned on time is different than 0.52 or is different than 52%. And that actually concludes 9.2 of our notes. So we are now ready to move into 9.3. As always, you can pause the video and finish writing your conclusion. But let's continue. So now we want to test a claim about a mean. So this entire time we were testing claims about proportions. Now we're ready to test claims about a mean. So we will only be covering this particular section when our population standard deviation is not known, okay? So you must meet certain requirements. The sample is a simple random sample. The population is normally distributed, or n is greater than 30. You've got to satisfy one of those conditions. Having said that, we are going to use the following test statistic formula. So T is equal to the sample mean subtracted by the mean of the sample means divided by the standard deviation. Now keep in mind, S is the sample standard deviation divided by the square root of n. So we will be using this formula to calculate our test statistic. In terms of finding the p-values, we're going to be using both technology and the t-distribution table. In class, we're going to pretty much stick to the t-distribution table. In your Lumen, you will be using a particular website that I provided for you. We're going to identify a range of p-values. This is very important to note, which can tend to be a little bit tricky, but I think once you see a few, you're going to feel just right. We're going to use a number of degrees of freedom to find the relevant row in the t-distribution table. And then we're going to determine where the test statistic lies relative to the t-values in that row. We're then going to identify the range of values using the area values given at the top of the t-distribution table. I know I said a lot, and I think once you see it, like I said, you're going to feel much better about it. Let's take a look at some practice problems. For each statement, use the t-distribution table, that's this one, to determine the range of possible p-values. So the claim is that for nicotine amounts in king-size cigarettes, mu is greater than 1.10 milligrams, where n is equal to 31. And the test statistic is t is equal to 3.349. The cool thing is lots have been given to you, right? So first thing to note is that our alternative hypothesis is that mu is greater than 1.10 milligrams. So we see right away that this is a right-tailed test. Just something to think about. I like breaking this kind of stuff down just so we have a visual in our minds. We see that if n is equal to 31, our degrees of freedom is always going to be one less. So our degrees of freedom is 31 minus 1, which is 30. What we're going to do, oh, and then also note here, we have our test statistic. So it was given to us that our test statistic, our t-value is 3.349. We want to figure out what is the p-value associated with all of this information. So we are going to go to the t-table with the row degrees of freedom equal to 30. So that's the first thing. So I'm going to show you what we're doing here. We're going to go to the t-table and we're going to find degrees of freedom 30. Here it is. Let me move this down. We were given our test statistic. Let me show that to you again. Your test statistic, your t-value is 3.349. So what I'm going to do is I'm going to look here at these values and say to myself, where does 3.349 fit? So if these are my values, my test statistics, I see that my 3.349 sits somewhere here to the left. Wow, I can't even talk. To the left of our value here, okay? So I'm going to write down, and you don't have to do this. I find sometimes it's really helpful. Your test statistic that you were given was 3.349. Now, keep in mind, this is a right-tailed test. So we're looking at the area in one tail. If I scooch up to the very top of the page, Notice that that refers to a probability that is less than 0.005. And that's because we're to the left of this test statistic. So in our first column, our test statistic is 2.750, but 3.349 is to the left. So the value to the left, or the area to the left, would refer to any p-value which is less than 0.005. Good. So we have just found the range of possible p-values. So we're going to say here that our p-value is less than 0.005. And that's it. We just have to find the range of possible p-values. Let's do that again. I know this can be a little bit tricky, so let's do it again. The claim is that for the tar amounts in king-size cigarettes, mu is greater than 20.0 milligrams. So first things first, the alternative hypothesis is that the mean is greater than 20.0 milligrams. Greater than, this is also a right tail test. Keep in mind that implies one tail, right? One-tailed test. If n is equal to 31, we see that our degrees of freedom is 30. This time, we have a test statistic of 1.7333. So we're going to go back to the t-table, and we're going to look up the row degrees of freedom 30. We're in the same row, but this time we have to figure out where that test statistic 1.7333 lies. Degrees of freedom 30. We're looking for 1.7333. So not in between here, not in between here. Aha. 1.7333 sits in between these two values. If we go to the very top of our chart, we see that that corresponds to a probability between 0.025 and 0.05. Remember that this is a one-tailed test, so you want to look at the probabilities referring to one tail. So our p-value sits between 0.025 and 0.05. So we're going to write a compound inequality, and we're going to do it like so. Our range of p-values is going to fall between 0.025 and 0.05. Perfect. Again, if you need to, please rewind the video, watch that again, but I have a bunch more examples just to show you exactly how we proceed. Okay, let's look at the next one. What if our test statistic was t is equal to 1.239? We still know that this is a right tail test. It's still one tail, right? One tailed test. We still know that our degrees of freedom are 30. So this time our test statistic is 1.239. Let's go to our chart. Degrees of freedom 30. Here we have it. We're going to go and look at each value and see where the heck 1.239 would fall. Still not here, still not here. Aha, 1.239 is beyond this value, right? It's to the right of this value. So we're going to go up to see that our p-value is actually going to be greater than 0.10. I want you to notice that your p-values increase as you move from left to right, okay? Your p-values increase as you move from left to right. So your p-value, since your test statistic is to the right of this last value, 1.239 is to the right of this last value, that means your p-value is actually going to be to the right of this 0.10, which means it's greater than 0.10. So let's write out that our p-value is greater than 0.10. Still having some concerns? Let's do some more. What I would highly recommend is you pause the video, try these on your own, replay the video, and see if your work compares or agrees with mine. 3A, The claim is that for measurements of standard head injury criteria in car crashes, mu is equal to 475 HIC, head injury criteria. The sample size is n is equal to 31. You're probably like, I'm over it. Why are we still using degrees of freedom 30? Because why not? So I'm going to make a note of that. Our degrees of freedom is 30. We're told that the test statistic is negative 2.242. We have to fix that, okay? First things first, what's our alternative hypothesis? Well, we weren't told less than or greater than. This implies not equal to. So we're looking at the claim that mu is not equal to 475 head injury criteria, HIC. Having said that, we recognize that this is now a two-tailed test. Okay, this is a two-tailed test with degrees of freedom 30. But when you look at your table, do you see that all of your test statistics are positive? No big deal. We are going to note that if our test statistic is a negative 2.242, we're going to look up in the chart the absolute value of that, which is a positive 2.242. So let's go back to our row of degrees of freedom 30, and we're going to look up where 2.242 lies. So degrees of freedom 30, 2.242, aha. 2.242 lies between these two values. So I'm going to write 2.242. I'm going to squeeze that in there, 2.242. That lies between these two values. This is now a two-tailed test. So because this is a two-tailed test, we want to look at the probabilities in that section at the top of the chart. So our probability lies within this range between 0.02 and 0.05. So that is a range of our p-values. Our p-values lie between 0.02 and 0.05. So let's write that out. 0.02 is less than our p-value, which is less than 0.05. Perfect. Do the same thing. Like I said before, pause the video, give this one a shot. We're using the same information, except this time our critical value, our statistic, our test statistic is negative 2.956. So go ahead and pause the video, replay when you're ready. We see that we're going to take the absolute value of negative 2.956 for a positive 2.956. Our degrees of freedom are the same. They're still 30. We know that we're working with a two-tailed test because we're using the information from before. Same thing, you're going to look for 2.956 in that row. Degrees of freedom 30, 2.956. Notice that's to the left of our value here. 2.956 sits to the left of our value here. So we're going to go to the top of the chart in the area where it says two-tail, and we see that our p-value is to the left of 0.01, which means that our p-value is smaller than 0.01. So our p-value is less than 0.01. So our p-value is less than 0.01. Beautiful. Again, same thing. I know this is a little repetitive, but it's going to be helpful. Pause the video, try this one on your own, replay the video. Your degrees of freedom are still the same. It's still a two-tailed test. I hope you're pausing the video and trying this on your own. Take the absolute value of your test statistic. That's going to be positive 1.298. You're going to go back to your table. Degrees of freedom equal 30. We're looking for 1.298. So degrees of freedom equal 30, 1.298. Let's go over 1.298, 1.29. Aha, 1.298 is to the right of our last value. So you go to where we said we have the information about the area in two tails. So it's to the right of this value. So it's going to be to the right of 0.20, which means it's going to be greater than 0.20. If your p-value is to the right of 0.20, that means we're actually bigger than 0.20. So let's write that out. Our p-value is greater than 0.20. Let me raise the screen so that you can see it. And voila, we have that completed. Okay, we have a couple more that you can try out. I would urge you to do these on your own for practice number 9. It's the same thing. You're finding the range of possible values. You're told that the claim is that for pulse rates of women, mu is equal to 73. Think about what the alternative hypothesis is. Note what the degrees of freedom are, use your test statistic, and find your p-value. Do the same thing for part B. So I'm going to leave these for you to try on your own. When I upload the notes, you will see these filled in and you can check your work. Okay, now we're going to put all of these ideas together. We're ready to do this. The ages of actresses when they won an acting award is summarized by the statistics. N is equal to 32. X bar, the sample mean, is 35.9 years. S, the sample standard deviation, is 11.9 years. And the significance level is 0.05. We want to test the claim that the mean age of actors when they win an acting award is 32 years. So I'm going to go ahead and highlight the claim. Sometimes it's helpful just to kind of make a note of what it is that we're looking for, especially since we're going to be running everything from beginning to end, checking the requirements, writing the null and alternative hypothesis, all that good stuff. Assume the sample was randomly chosen. Let's write out some information. If N is equal to 32, your degrees of freedom is 31. It is one less. You're told that the significance level, your alpha, is 0.05. Good. You know that your mean, your sample mean, is 35.9 years, and you know your sample standard deviation is 11.9 years. So let's check the requirement. You are told that the sample is randomly chosen. So we can make a note that, yes, we can check off random. We're not told that this population is a normal distribution, but what we are told is that N is greater than 30. N is greater than 32. So that actually satisfies that second condition. N is greater than 30. Perfect. We're now ready to write the null and alternative hypothesis. So consider that the business as usual, our null hypothesis, is that the mean age of actors is 32 years old. So that implies that our alternative hypothesis must be that the mean is not equal to 32 years. So we see right away that this is a two-tailed test. Perfect. We're going to go ahead and turn the page and continue with this information. The next thing we're going to do is we're going to calculate our test statistic given the information that we were provided. So we want to calculate the test statistic using the following formula. T is equal to the sample mean minus the mean of the sampling distribution over the sample standard deviation divided by the square root of N. Good. So we're going to fill in our information. From the previous page, and I'm just going to scoot this over so that you can see, our sample mean is 35.9 minus our mean is 32. So we're going to be using this information here. Our mean is 32. Divided by the sample standard deviation, which is 11.9, over the square root of N, and N in this case is 32. We have that right here. So N is 32. Perfect. When you plug all of this into your calculators, you see that your T statistic is 1.855. And you can verify that for yourselves when you punch this into your calculators, 1.854. The next step is to determine the range of values for the p-value. So it's going to be helpful to note that the degrees of freedom are 31. It's a two-tailed test. And our test statistic is 1.854. So we're going to go to the row where degrees of freedom is 31. Here we have 31. We want to look up 1.854. So we keep going, 1.854. Aha, that's between these two values. It is a two-tailed test. So if we scroll up to those p-values, we see that our p-value lies between a 0.05 and a 0.10. That is a range of values for the p-value. So we will write 0.05 is less than our p-value, which is less than 0.10. Now we have to compare the p-value with our alpha. We are still doing this. So we want to compare the p-value with our alpha. Keep in mind that from our previous page, we saw that our alpha was 0.05. But we see that our p-value lies between 0.05 and 0.10. So what we can do is we can say that our upper bound, which is 0.10, is definitely greater than our 0.05. Also, by analyzing this particular interval, this compound inequality, when we analyze this interval, we know that our p-value is definitely bigger than 0.05. We see that here. It's greater than 0.05, but it's smaller than 0.10. So our p-value is definitely greater than alpha. So our decision is to fail to reject the null hypothesis. We are now ready to write our conclusion. So I'm going to write that right next to it. I'm going to pause the video so that I can write this down and you can copy. So for our conclusion, we can state there is not sufficient evidence at the 0.05 level of significance to show that mu is not equal to 32, or that the mean age of actors when they win an acting award is different from 32 years old. There is not sufficient evidence to show that that is the case. Okay, we failed to reject the null. When we decide what type of error, remember we're going back to our magical formula, our magical chart on page 4. If you take a look at page 4, notice it says, if you, and then we failed to reject the null. So if you fail to reject the null, we could have made a type 2 error, which means the null hypothesis was actually false. Okay, so let's write that down. We could have made a type 2 error, which means it could have been true that the average age, you could say mean age, average age, that the average age was not equal to 32 years old. Because remember, we failed to reject the null. So because we failed to reject the null, we could have made a type 2 error, which means it could have been true that the average age was not equal to 32 years old. Perfect. Let's go ahead and turn the page. A seismologist measured the depths of a sample of 600 earthquakes. She found the average depth to be 5.82 kilometers. That's actually really important to note. X bar is equal to 5.82 kilometers. I also want to note that the sample is 600 earthquakes, so N is equal to 600. with a standard deviation of 4.93 kilometers. So S is equal to 4.93. Using a level of significance of alpha is equal to 0.02, here's my highlighter, test the claim that these earthquakes are from a population with a mean equal to 5.00 kilometers. Assume the earthquakes were randomly chosen. Awesome. We see that it's a random sample. Beautiful. And we also see that N is bigger than 30 because it's 600. So even though we're not told that it comes from a normal distribution or that the population is normally distributed, we see that N is greater than 30. So that satisfies the requirements. Our null hypothesis, our business as usual, is that the mean is equal to 5.00 kilometers, which implies that our alternative hypothesis is that the mean is not equal to 5.00 kilometers. We can write down that this is definitely a two-tailed test. We want to calculate the test statistic. So we have T is equal to the sample mean, which is 5.82 minus the population mean, or essentially the mean of the sampling distribution of sample means, that is 5.00, divided by the sample standard deviation over the square root of N, and N in this case is 600. When you compute these values, you should have a test statistic equal to 4.074. We are going to note that our degrees of freedom, if N is equal to 600, our degrees of freedom is one less. So our degrees of freedom is equal to 599. Yes, I said it, 599. Keep in mind, this is a two-tailed test. And we know that our test statistic is 4.074. So we want to go to our table. And we essentially want to know, where are my degrees of freedom 599? So I'm going to show you something. Notice we have degrees of freedom 500 and degrees of freedom 750. If you're ever wondering which row do I have to go to, you want to go to the row that you're closest to. So degrees of freedom 599 is going to be closer to 500 than it is to 750 for sure. So we're going to be in this row of 500. Recall that our test statistic is 4.074. When I look at these values, I see right away that 4.074 is to the left of the highest value here. So we're to the left of this first column. This is a two-tailed test. So we want to go all the way to the top of the chart, and we want to look at the area in the two tails, 0.01, and we see that our p-value, our probability, is going to be smaller than 0.01. So our p-value is going to be to the left of 0.01, which is smaller. So let's write out that our p-value is less than 0.01. We are now ready to compare the p-value with our alpha. As a reminder, our alpha was 0.02. So we are ready to state our decision and conclusion. Compare your p-value with your alpha. Your p-value, notice, was a value less than 0.01. So we can write 0.01 as the upper bound. Our alpha is 0.02. Right away, we see that our p-value is less than our alpha. So we can say, all right, let's reject the null. Give a shot at writing the conclusion based on this decision. And then you can compare your work with mine. Pause the video and then come back when you're ready. We see our conclusion as that there is sufficient evidence at the 0.02 level of significance to show that mu does not equal 5.00 kilometers, or that the earthquakes are from a population with a mean not equal to 5.00 kilometers. At this point, we're ready to discuss the type of error you could have made and what it means. So you're going to go back to that chart on table 4 and determine the type of error. Using the table, you would find that we could have made a type 1 error, which means it could have been true that the earthquakes were from a population with a mean equal to 5.00 kilometers. And that concludes practice number 10. We're going to continue through this process. Practice number 11 is very, very similar, with practice 12 being the mini tab printout, same with practice 13. What I'd like to do at this point is I would like you to work on practice number 11. I will, as always, fill in the notes, and then I will send this to you. I'll place this on Lumen so that you can have my filled in work. But I would like you all to try practice number 11 on your own and then check to see if your work agrees with mine. So having said that, let's move on to practice number 12. Interpreting a mini tab printout. In a manual on how to have a #1 hit song, it is stated that a song must be no longer than 210 seconds. That makes me think of Bohemian Rhapsody, right? Where they totally discredited that. A simple random sample of 40 current hit songs results in a mean length of 240.4 seconds and a standard deviation of 56.29 seconds. Use a 0.05 significance level, so I'm just going to write that out because that's going to be helpful, to test the claim that the sample is from a population of songs with a mean greater than 210 seconds. So notice here we have our null hypothesis and we have our alternative hypothesis. Although it's not completely stated, it would be mu is greater than 210. So here we have our mini tab printout. We have our test statistic, our t-value, right, which is 3.42. That's kind of interesting and it's helpful to us, but we actually don't need that because we were given the p-value in this case. So we're going to go ahead and write the null and alternative hypothesis, which is really nice because that was presented to us. So we see that mu is equal to 210. And the alternative is that mu is greater than 210. And this is 210 seconds. So I'm going to write seconds for both of these, just so that we see the units that we're referring to. Greater than, right? That implies one-tailed specifically. This is a right-tailed test. That means we're looking at one tail. Good. We are going to state our decision about the null hypothesis and explain how you reach your decision. Same exact thing, everyone. We compare the p-value and the alpha. I feel like at this point, you're all super proficient at comparing the two and then making a decision. So we see that our p-value is less than our alpha, so we are definitely going to reject the null. It's nice because even though you haven't seen this before, I know for a fact that you know exactly the steps that follow. So we're ready to write the conclusion. Our conclusion in this case is that there is sufficient evidence at the 0.05 level of significance to show that mu is greater than 210 seconds. The population mean length of hit songs is greater than 210 seconds. When you go ahead and turn the page, we have one more mini tab printout. I will go through this last one with you just to make sure that you're okay, but honestly, I feel like you're going to be just fine. So if you'd like, pause the video at this point, try these on your own, and then play the video and see how it works, okay? The first thing we're going to do is we're going to check the requirements. Notice that we are told the random sample, right? So we can say random. Also notice we're told that the population was normally distributed. So normally distributed. Even though our n is actually less than 30 in this case, we have to be told one or the other. Either it comes from normal distribution or that n is greater than 30. We were told that the population is normally distributed, So that satisfies our requirement. We want to identify the test statistic and the p-value. Looking at our printout, we see that our test statistic, t, is equal to negative 1.04. Our p-value is 0.300. Let's go ahead and note those values. We want to state the decision about the null hypothesis and explain how you reached the decision. Keep in mind, your null hypothesis, if you would like to write this out, is that your mean, your mu, is equal to 18, where your alternative, notice it says not equal to 18. Good, perfect. We are going to compare the p-value with our alpha. If you're wondering what your alpha is, look at your confidence interval percentage. You're told 95% confidence interval, which implies that your alpha is 5% or 0.05. So we are going to compare our p-value with our alpha. Our p-value is 0.300. Our alpha is 0.05. We see that our p-value is greater than alpha, which implies we fail to reject the null hypothesis. We're ready to write our conclusion. Mind you, we aren't given any information about what the 18 means. Are we talking about 18 seconds, 18 meters, 18 whatever? We're not told any of that information. So we can simply state that there is not sufficient evidence at the 0.05 level of significance to show that mu does not equal 18. And that's exactly what we're going to write here. Next, we're ready to discuss the type of error we could have made and what it means. So again, when you go to page number 4 and you use your chart, notice we failed to reject the null. This implies we could have made a type 2 error. So think about what we're saying. We failed to reject the null, right? So that kind of means like we accepted it. So it could have been true that the mean was not equal to 18. So that's the type of error we could have made, and that is exactly what it means. So let's write that out. And there you have it. That concludes our Unit 9 notes, which, by the way, also means we have finished the course. Congratulations on sticking with it and completing everything thus far. Make sure that you are studying and creating a formula sheet to help you to have all of those formulas and concepts together in one central location. That's going to be incredibly helpful to you as you study. Formula sheet first, then go through the review packet. Next week, we'll be reviewing together and making sure that you're all ready for the final exam. All right. Enjoy the rest of your weekend. Good luck. You can do this. Bye, everyone.